All right, we're about to begin. I have a lunch with the president that I have to go to. I'm going to try to wrap up a little bit early. So we're probably going to wind up being a whole lecture behind after I finish up what I want to talk about today. Yep. As some of the people over here on this side of the room were discussing, this class does indeed have homeworks. You should expect to receive your first one at some point today or tomorrow, and it'll be due next Thursday. Okay. Yeah.
Oh, yeah, I know. Yeah, sure.
It was, and indeed.
I'm so upset.
All right, let's see if this thing actually works today.
One class that did have homework until now.
So pretty.
They both didn't have to do anything in my classes and pass today. Like, you know what I mean?
Well, that's why why would you be calling about that? You're just paying for it.
I'm paying to soak in the knowledge. I'm paying to soak. I'm soaking. That currently soaking. I'm dreaming.
I cannot say this conversation that's going on right now, and I know Dr. Hartman is on here.
I just want this fucking projector to work so I can do my job.
That's not even soaking anymore. You're out of tub. You got soaking.
All right. So today we're going to be talking. Oh my God, you guys are so fucking loud. Hey, class stuff. So today we're going to be talking about air gaps in magnetic circuits. So I believe I've mentioned this previously, but air gaps are a way, whether intentional or unintentional, to significantly increase the reluctance of a magnetic circuit. So we use air gaps for a couple of different things. In energy storage devices like inductors, air gaps effectively help us make it more difficult to reach what's called saturation, which is something we're going to talk about probably in our next class meeting, which means effectively that we can store more energy before our core becomes so magnetized that it can no longer change and we can't put any more energy in. Air gaps also tend to linearize the permeability of a material. Again, this is something that we're going to talk about probably on our next class meeting when we look at magnetic domains and all of that kind of good stuff. And then when we have rotating electrical machinery or things like relays and stuff like that, an air gap is a functional part of the system, meaning we can't have a machine, we can't have our rotor rotate and our stator be stationary without an air gap to physically separate those two systems from each other. Likewise, in an electromechanical relay, there's going to be an air gap between the portion of our relay that moves to close the contacts and the remainder of the magnetic circuit. And if that weren't there, we wouldn't have a relay. We'd just have an inductor or a transformer. All right. So I'm going to draw a core with an air gap here really quickly. And I want you guys to note that the air gap in this particular figure is greatly exaggerated. Typically speaking, they are very, very small, so that we don't have a whole lot of flux leakage. Okay. So we've got this kind of C-shaped core. Actually, let me make that gap even bigger so that I can draw things better. Sorry about that. So here's our C-shaped core. This region of space here in the middle is our air gap. And because it is not our magnetic core material, excuse me, it is going to have a different permeability. So air's permeability, mu, is pretty much just the same as the permeability of free space, okay? And then over here, we have our core material. And we're going to say that its permeability is mu c, which is typically speaking hundreds, if not thousands of times larger than the permeability of free space, dependent on the material that we choose to use for our core, okay? So this dimension is going to be the length of our air gap, which I'll call it simply L subscript G. Okay. We've got our thickness, T, and then we have our other dimensions of our core that we'll talk about in a little bit. So let's say that I wrap a coil around this core using the same winding that I have done every other time. And I'm passing some current I through here, and our coil has N number of turns. Okay. So if the air gap length LG is small, so let me write this down really quickly. So if LG is small, and by this I mean smaller than the dimensions of the adjacent core faces, then our magnetic flux phi b will follow the path defined by the core. And the air gap can be treated as a reluctance in series with the core material. Okay. So when we were talking about permeability and all that kind of stuff a few days back, one thing that I believe I had mentioned was that the higher the permeability of the material, the easier it is to magnetize, and effectively the more concentrated the magnetic field lines are, right? So realistically, we want our cores to have as high of a permeability as possible so that we don't have magnetic flux leakage. Well, if we introduce an air gap, we now have an opportunity specifically for magnetic flux leakage. So we kind of need to take that into account a little bit. So I'm going to draw a picture here, and this is kind of a close-up of what's going on in the air gap, okay? So this is part of our core. Like so. And these squiggly lines are just saying I'm cutting this off because I'm not interested in what's going on elsewhere. And I'm going to have something fairly similar down here as well, right? So between these two faces of our core is our air gap. So I believe I've been doing our flux lines in this kind of light blue color. So what we should see is that through the center, the path of our flux lines is effectively uninterrupted. But as we move away from the center of the face of our core, where there's an air gap, we're going to see that things start to spread. Until we get to a point like so, where we're going to have what are called fringing fields that extend outside of the normal flux path. Like so. So essentially what we've got here is our magnetic flux is seeing a larger effective cross-sectional area, okay? Because we're allowing it to spread out because its path isn't fully defined by the core anymore. So what do you guys think would be a consequence of our flux seeing a larger area? Our magnetic flux density vector B has to go down, right? Because the cross-sectional area is larger. So how we are going to typically compute the effective area of our air gap is as follows. So the area of our gap will be equal to the thickness of our core face plus LG, and that looks awfully a lot like a Q, so let me redraw that, times the width of our core face plus LG. So we're effectively just going to increase the dimensions of our core face by the length of the gap. And so obviously, the larger the gap is, the more area we are seeing, and the weaker our magnetic flux density will be.
Yeah, big old paragraph. Maybe just take a picture of that.
It's going to be on the video whenever I get around to posting it, probably this weekend for what it's worth. All of that paragraph says essentially is when there's an air gap, we treat it as a reluctance in series with the
That's
core.
where we're right then.
Yep. All right, so let's work a simple problem and then we'll do our in-class assignment and then we'll actually kind of wrap things up here, okay? So
You said we treat it as a reluctance.
yes. So this structure that I'm about to draw is a simplistic representation of at least the magnetic portion of a relay, okay? So we're going to have kind of a horseshoe-shaped core. Like so. And then we're going to have a second section of our core over here. And then these two sections of core are separated by some air gap. So if we were to put a coil around this leg, where I is flowing in and coming out in this direction, here's N. Based on the way that I have this thing wound, we should expect our flux to kind of follow this loose path, right? So our flux is going to see those air gaps, and once we talk a little bit more about electromechanical energy conversion, we're actually going to be able to figure out the attractive force between these two sections of core, or how much force or voltage or current we need to apply in order to cause a relay to close. But for now, we'll just say that these two separate things are fixed and we're not worried about that, okay? So let's throw some dimensions on this thing. let's say that this is some width W, and it's also some width W here, and this section over here also has a width W. The thickness, so the direction into the board, let's call that T, is going to be 1 centimeter. The width is going to be 1 centimeter. So we have a uniform square cross-sectional area. Okay. Let's call this length up here L1, where L1 is 8 centimeters. Let's call this length here L2, where L2 is 4 centimeters. And this section also has a length of L2. And lastly, let's define our air gap distance here, LG, is equal to 0.5 millimeter. So this is grossly exaggerated for clarity's sake, but the air gap in this case is very small, significantly smaller than the faces of our core, right? So the face has dimensions of 1 centimeter by 1 centimeter. 0.5 millimeter is obviously much smaller than that. So this should still function pretty well as a magnetic circuit. Let's also say that mu C is 1,000 mu naught. And what we want to find is the, let's say that we have a flux phi B of 100 microwebers in the core, and we're trying to find the MMF, or the magnetomotive force, necessary to sustain that amount of flux in this magnetic circuit. Okay. So I'm going to treat this effectively as if it were two reluctances connected in series. Actually, before we even do that, let's remember our relationships, right? So MMF is equal to flux times reluctance, right? That's our Ohm's law for magnetic circuits. We're trying to find MMF. We're given a flux, so we just need to figure out what the equivalent reluctance of this magnetic circuit is in order to find the MMF that would be needed to sustain it. Or if I had given you a value of N, we could then figure out the current needed to sustain that flux, et cetera, okay? So I'm going to treat this magnetic circuit as two reluctances in series, where one reluctance is for the core itself, and the other reluctance is for those two air gaps. And I'm just going to lump them together as a single equivalent reluctance there, right? So let's start with the core, okay? So remember that our general expression for reluctance is L over mu A, where L is the average length of the flux path as it travels through the core. So what do you guys think that would be? So let's break things down here really quick, right? So we've got
Wouldn't it be 2L1 plus L2?
so let's break things down into a little digestible bit so we can figure things out. Okay, so I drew this purple line. Hopefully it shows up as purple right here. Okay, so this is definitely part of the flux path. So what is this part going to look like? L1 minus half of a W, right? So we're going to have L1 minus half of a W. And then we are absolutely going to multiply it by 2 because that is the exact same length on this bottom leg right here, okay? Then we have this guy right here. So is that a full L2?
L2 minus half.
So it's L2 minus a whole W because it's going to be a half a W on the top side that we're not going through and a half a W on the bottom side that we're not going through. So plus an L2 minus W. And that should also be multiplied by a factor of 2 because of this guy right here. And then now we've got to take into account that little piece. Well, what is that? That's just half a W. And then we're going to twice that. Yep. So plus, let's just call it, just for the sake of argument, I'm going to write it down as plus 2 half W. And then we'll pretty this up here in a moment. Okay. So what's the permeability of our core? Mu C, which is just 1,000 mu naught. So I'm going to write it as 1,000 mu naught. And then what is the cross-sectional area of our core? So the width times the thickness, which is absolutely just going to be 1 square centimeter. Absolutely right. So I'm just going to write it as WT for now. And let's pretty this business up here, right? So I've got a twice L2. Excuse me, L1 plus L2. Let's see, I've got a minus W from this guy and a plus W from this guy. So those guys cancel out. So I should just have minus 2W from this term here. Does that make sense? We all okay with that? All right. Divided by 1,000 mu naught times W times T. And we'll throw some numbers in here really quickly, right? So 2 L1 plus L2 is going to be 12 minus W is going to be 11. So 11 centimeters. We all okay with that? L1 plus L2 minus W, because there's a common factor of 2. So I could literally just, instead of having it like that, the same thing. So L1 plus L2 is 12, minus 1 is 11.
Okay.
Multiplying that by 2 will wind up giving us 22. Okay. Over 1,000 times 4 pi times 10 to the minus 9 henries per centimeter. And then our area is 1 centimeter squared. So I'm going to throw this into my calculator. Excuse me. 22 over 1,000 4 pi times 10 to the minus 9 times 1. And I get 175,000, excuse me, let me just do it like this. 1.751 times 10 to the 6th amp turns per Weber. This reluctance for our core is a good bit higher than the reluctances that we've seen in our previous examples. Can anybody think about why that might be? So we haven't taken into account the air gap at all yet, right? This is just of our core. Okay. So there are 2 reasons. The first reason is that our area is only 1 square centimeter. We've been dealing with larger core sizes. So if our area is larger because it's in the denominator, that's going to make our reluctance smaller. Also, our permeability is only 1,000 mu naught when I think we were using 2,000 and 5,000 and things like that last time. So a lower permeability is also going to cause our reluctance to go up. Okay. So 1.751 times 10 to the 6 amp turns per Weber is just the contribution from our core. Now, let's figure out what's going on with our air gap, right? So what is the total length of our air gap? 2 LG, because we have two identical air gaps, right? So twice LG. What's the permeability of our air gap? Because it's air, it's just mu naught. And then our cross-sectional area for our air gap is going to be the width plus LG times the thickness plus LG. So when I put numbers into this thing, I have 0.5 millimeter times 2, so that's 1 millimeter. And a millimeter is 1/10 of a centimeter, if I'm remembering correctly, which I strongly believe I am. Mu naught is just going to be the 4 pi times 10 to the minus 9 henries per centimeter. Our width is now going to be 1.05 centimeters. So that's 1 centimeter plus 0.5 of a millimeter. And then our thickness is going to be the same thing. So I'm just going to square this. Are we all okay with where those numbers came from? All right. And so when I throw this into my calculator, I have 0.1 over 4 pi times 10 to the minus 9 times 1.05 quantity squared. And I got 7.218 times 10 to the 5 amp turns per Weber. Okay. So even though we only have a total air gap length in this magnetic circuit of 1 millimeter, which is significantly smaller than the core length of 22 centimeters, our reluctance is damn near half of what we're getting out of the core, just because that permeability is so much smaller. Sorry, let me text Dr. Batari real quick. All right, so adding these two together, our equivalent reluctance is just what's seen in the core plus what's seen in the gap. So answer plus that. Oh, I'm dumb.
Is it the six?
Yeah.
Yeah, that was what I was getting. I was just really afraid of it.
No. I just miscounted the number of digits. Nope. So that means that's even worse, right? So our air gap, even though it's so short, has about 6 times the reluctance of our core material, right? So our total reluctance here is then 8.969. Sorry, I couldn't count the number of digits correctly. You'd think with a PhD I could count to 6.
It's really hard these days.
Amp turns per Weber. All right. So from here, our MMF is simply our flux, which was 100 microwebers, or 100 times 10 to the minus 6 Webers, times our reluctance of 8.969 times 10 to the positive 6 amp turns per Weber. Gives me a value of 896.86, rounding up to 2 amp turns of MMF needed to pass 100 microwebers of flux through this magnetic circuit. Okay, so let's circle back around to in-class assignment 2, problem 2. We'll finish that up and then we will call it a day since I have other things I've got to take care of today. I'm sure you guys are absolutely distraught that you get out of class early and get to have lunch.
Just so unbelievably upset right now.
Yeah, well,
I want to do every lecture today. I want to be here till 6 p.m.
we would be here till probably 6 p.m. Sunday if I did them all.
And look, that's okay, you know, we get all out of the way.
So I don't know what time you would have.
As long as we get like, as long as we get breaks every like 3 to 4 hours to let the dogs out.
Yeah.
I can.
All right, so for this particular problem, we have a very simple representation of a rotating electrical machine effectively, all right? So this would be an example of something like if this were our stator and this guy right here were what's known as our rotor, this would be effectively a synchronous machine, right? So if we allow that middle bar to spin, we actually have some sort of, actually this would be a generator because I'm mechanically spinning the thing in the middle and generating electricity on the outside. But anyway, so we have a rotor length of 50 centimeters with a particular cross-sectional area of 100 square centimeters. The stator has an average radius of 56 centimeters and a cross-sectional area of 100 centimeters squared. And the material for which the rotor and stator are made has a permeability of 50,000 mu naught. So this is a really good ferromagnetic material. Our air gap length is 1 centimeter and our air gap cross-sectional area is 125 centimeters squared. And we are asked to determine the magnetic flux density inside the rotor if our MMF is 10,000 amp turns. Okay, so ultimately we are trying to find B. Okay. So what is our relationships dealing with B, our magnetic flux density? I'm unsurprised.
There,
Um,
my aunt was asking me Christmas. Okay.
all right, so we're trying to find magnetic flux density B, okay? So what are our equations for B?
Oh, theta B over A.
Okay, so phi B,
5
our magnetic flux over our cross-sectional area. I'm gonna put B rotor here and A rotor here so that we know what we're looking at. Okay, so our cross-sectional area of our rotor was given to us. It's 100 centimeters squared. So if we can find our magnetic flux passing through our rotor, phi B, then we should be good to go. Well, phi B,
Do we have a number of turns?
we don't have the number of turns, but we do have MMF, right? So if I'm not mistaken,
That's,
MMF over reluctance. Right? So just as a heads up, the thing that we used a moment ago was MMF was equal to phi B.
oh, okay. Oh, yeah, this is our basically like our own.
Ohm's law, exactly right. So if I want current, I divide MMF by reluctance. Or when I say current, I'm talking about the flux, right?
Yeah. Because the flux is the current.
Yep. MMF is the voltage and reluctance is the resistance. Absolutely right. It's just Ohm's law. That's 100% correct. Okay, so MMF was given to us. So this is once again, once we find the equivalent reluctance, we're off to the races and we can do everything else within a step or two, okay? So we've got a core, or excuse me, we've got a rotor that's going to have reluctance. We've got an air gap that's going to have reluctance. And then we've got our stator, which is going to have reluctance. So we can simply just add those two guys, or add those three components together, okay? So let's figure out the reluctance of the rotor first. So just using our basic L over mu times A equation for reluctance, which is the only thing we've got to go with. What's the length of our rotor? 50 centimeters, absolutely right. What is the permeability? 50,000 mu naught. So that's 5 times 10 to the 4. That's 50,000. 4 pi times 10 to the minus 9 henries per centimeter. What's our area? 100 centimeters squared. Sorry, I shouldn't have put the square there. And so if I plug this into my calculator, 50 over 50,000 times 4 pi times 10 to the minus 9 times 100, I get 795.775 amp turns or Weber. Owen, did I screw anything up this time? Good deal. All right, so let's talk about the stator, okay? So I've tried to illustrate it on the figure here, but as our magnetic flux is generated by this coil, it's going to flow through the rotor and then the air gaps, and then it's going to hit the stator, and it's going to have two identical paths, one to the left and one to the right. So realistically, we could treat that as if it were the reluctance of the left-hand path in parallel with the reluctance of the right-hand path, which, since they're identical, is just going to be half the reluctance of the left-hand path or half the reluctance of the right-hand path. So I could start off by saying that our stator is going to be equal to 1/2 times something, okay? So what is that length going to be? So it's the radius of the stator, but it's not going to be 2 pi, it's just going to be pi, because 2 pi would be going all the way around the circle, but we only need to go halfway around the circle. So 56 centimeters times pi. Our permeability is the same thing as it was for the stator, because it seems like the stator and the rotor were made of the same material, which is fairly common. So 5 times 10 to the 4, 4 pi times 10 to the minus 9. Area of the stator is also 100 centimeters squared. So I'm going to throw this into my calculator. Sorry, let me close that bracket there. So 0.5 times 56 times pi divided by 50,000 times 4 pi times 10 to the minus 9 times 100. So I got this to be 1,400 amp turns per Weber. Anybody else get a similar result? Good deal. Lastly, we have our gap. So there are two air gaps in this magnetic circuit. We have one up here and one down here. So we're going to use twice our length, which would be, in this case, 2 centimeters in total. So twice LG, so 2 times 1 centimeter. What's the permeability of our air gap? Always mu naught. 4 pi times 10 to the minus 9 henries per centimeter. And then our area was given as 125 centimeters squared. So 2 over 4 pi times 10 to the minus 9 times 125 gives me 1.273 and some change times 10 to the 7 amp turns per Weber. So how does the reluctance of our air gap compare to the reluctance of our stator or our rotor? About 1 million times larger, right? Pretty damn big. So for a lot of rotating electrical machinery and all that kind of stuff, if we build that machine out of ferromagnetic material, which has a very high permeability, the only reluctance that's actually going to contribute to anything is the air gap itself. That's actually how they design reluctance motors, which are the new motors that are used in newer Teslas and all that kind of good stuff. It's a pretty interesting scheme where effectively it uses, excuse me, I hesitate to call it magnetic attraction, but effectively the properties of reluctance are such that it's always trying to minimize it. So it's dragging the rotor around to try to make the area of the air gap larger at all points and times. And you just tune that to energize coils in a specific pattern, and it's constantly pulling the rotor around in order to minimize the reluctance. So it's a reluctance-based machine. Pretty neat. Yes.
I've heard about that. Isn't that basically a stepper motor?
That's what I was going to say. I'm pretty sure stepper motors are not the exact same as that, but they do use magnetic, pulses to do the steps. Which is
Yep.
how
I'm not 100% sure on how stepper motors operate, other than that they do operate in distinct steps, whereas these reluctance motors are more a continuous rotation thing. But that concept of energizing coils in a fixed pattern is a very common way to use motors. So your DC brushless motors actually work in a very similar way. You have a whole bunch of coils in your stator, typically 6 coils in your stator that you can energize at particular times using what's called an electronic speed controller, which is just a fancy set of transistors and all of that kind of stuff that are timed in a particular way. So energizing the coils causes magnetic attraction, which effectively drags the permanent magnets that are affixed to the stator, or excuse me, the rotor, which is on the outside for most brushless DC machines. So it's using magnetic attraction to pull it around. And then it also uses the back EMF to push as well, so that you get more efficiency out of that system. So I think stepper motors are something more similar to a brushless DC, but I honestly haven't looked into it, so I could be totally wrong. Yes.
I could be wrong, but I think we threw an extra 10
Perhaps.
onto the final answer for this. Counted a couple.
Oh, nope, yep, damn it. 10 to the 6. Son of a bitch, I can't count to save my life today, but either way, it's still ridiculously larger is the point that I was trying to make here. All right, but it would have messed with our calculation at the end. So thank you, Owen, for catching me at making asinine simple math mistakes today. No, you get, I encourage it. I would much rather you guys learn the correct thing than just be like, hey, he probably knows more than me. Anyway, all right. So we've got our reluctance. We know our MMF. So our rotor, excuse me, magnetic flux density is just going to be MMF over reluctance times the area of the rotor, right? So our MMF in this case is 10,000 amp turns. The area of our rotor is 100 centimeters squared, because Tesla is usually expressed, or not usually, it is expressed as Webers per meter squared. I'm going to go ahead and do a conversion here where 1 meter is 100 centimeters and square that guy. I'm only going to bother putting in the 1.273 times 10 to the 6 amp turns per Weber here because the other things are so much smaller that they're not going to really do anything. So 1.273 times 10 to the 6 amp turns per Weber. And just to make sure everything's on the up and up, let's look at our units here really quickly. So I've got amp turns in the numerator, and then I've got amp turns in the numerator of the denominator. So those guys cancel each other out. I've got 1 over Weber, so that's going to wind up putting a Weber up here. And then my centimeter squared cancels these guys, so I'm going to wind up with Webers per meter squared, which is a Tesla. So all my units are just going to work out okay. So 10,000 divided by 100 over 100 squared times 1.273 times 10 to the 6th. I wound up getting 0.786 Tesla. So a little bit of rounding error, but not a whole hell of a lot. All right, so that's where I would like to stop for today. So enjoy the extra hour of your day of not putting up with my bullshit. Yeah. All right, thank you guys for your attention. I'll see you on Tuesday.